In this video, I want to look at the midpoint-connector theorem, both for triangles and for trapezoids. The midpoint-connector theorem for triangles says in any triangle, the segment joining the midpoints of two sides of a triangle is parallel to the third side and has length 1/2 that of the third side. We're going to let L be the midpoint of AD, where D is the foot of A on line BC. So let's draw some quick pictures of this. We have a triangle that we'll call ABC. We're essentially going to draw the line that's perpendicular from A to segment BC. This will be the point D, this intersection point, and L will be the midpoint of that segment. And there are two possible cases here. We have a case that looks like this up here, and then a case where it needs to go on the extended segment. So something like this, where we have A, B, C. We need to extend out the side BC and draw our perpendicular down. So that will be point D, and then once again, L will still be the midpoint of this segment AD. I'm also going to let M be the midpoint of segment AB. So here are my two values for M. I'm also going to let N be the midpoint of segment AC. I know that lines ML and line LNL are parallel to segment BC, and this is because now I have a right triangle, and I've already discussed how this thing is true for right triangles. Since there can only be one parallel through my point L, I know that these two segments have to be on the same line. So therefore, while it doesn't look that way in my picture, line MN is going to be parallel to line BC in both of these. So that gives us the first part. The second part wants to look at the length. For this first case here, we have that MN is equal to ML plus LN. By the fact that these are each right triangles, this is 1/2 BD and 1/2 DC. That's the same as 1/2 BD plus DC, which is 1/2 BC, which is exactly what we need. And we can do a similar argument for this triangle down here. And now I want to look at the midpoint-connector theorem for trapezoids. In any trapezoid, the segment joining the midpoints of the two legs is parallel to either base. It has length 1/2 the sum of the length of the two bases. Let's start by drawing a picture of a trapezoid. Here we go. And we'll call this ABCD. We want to draw the segment that connects the midpoints. We'll call these midpoints M and N. And I'm going to further go ahead and divide this up by drawing this segment BD. And I'm going to let this intersection point here be L. If L is the midpoint of my diagonal BD, then we can apply the previous theorem to triangle DAB and triangle DCB. In this case, we would have MN is equal to ML plus LN. We already know that ML would be 1/2 the length of AB. And we know that LN would be 1/2 the length of DC, which gives us what we want. So if L is the midpoint here, then we can just use our previous theorem to get that this is parallel to each of the bases, and that the length of MN is 1/2 the sum of the bases. This is a little bit more complicated to do if L is not the midpoint of BD, so I won't prove that case, but it does still hold.